Okay, so here's where we left off last time. So we talked about partial derivatives, a lot like single variable derivatives, really. I mean, in terms of the computation. In fact, I put forth partial derivatives as the easiest derivatives to compute. They're even easier than single variable derivatives, because when you're computing a partial derivative, let's see, let me find a conspicuous, there we go. When you're computing a partial derivative, before you get started with the process of applying all of your same rules, chain rule, product rule, etc., you get to say, you know what, I'm just going to treat large fractions of this function as if it's constant. All right? So it's even easier from a certain point of view than computing single variable derivatives. So that's super convenient. So anyway, being a lot like single variable derivatives, hopefully no surprise you can take a second partial derivative, just like you can take a single variable second derivative. So, for example, notice if you have a real valued function of several variables, when you take its partial derivative, the result is also a real valued function of several variables. It's the same kind of critter. So you can talk about taking a partial derivative of this new function, which itself is already a partial derivative. So second partial is what we call it. The notation's pretty reasonable. This is how we denote taking the x partial of the x partial of a function. Right? This is how we denote taking the x partial of the y partial of a function, etc. Now there's another notation along these lines. This notation here you should be aware of. It's extremely common. It's far more common, in fact, than, so this is what you're going to see in practice for a second partial. And this always used to bug me because this square here, we're not really squaring. It's not like there's this little partial symbol that's being multiplied by itself. It's not, right? It's just notationally suggestive, right? This is intended to be notationally suggestive of what you're seeing right there. So that's all it is. But it's always kind of irked me a little bit. And there is another notation. Let's see, where did I write that? Where did I put that? Well, let me just show you another notational alternative to this. Recall that when you take a partial derivative, sort of the Newtonian notation is to just put a subscript of, what are you taking the partial with respect to? And so if you're then taking a partial of that, you put another subscript. So, okay. All right. So now that's all algebra. If you have this algebraic thing, you can do this algebraic process to it. Yeah.
Are there going to be functions where we're going to get different results if we first take partial?
Yeah, you're getting a little ahead of me. The answer is that such examples exist, but they're very rare, and we're not going to have to really worry about it. But I'm going to get to that in a few minutes. Yeah. Okay, so we have this algebraic discussion here of if you algebraically take a function, apply certain algebraic rules. How do you denote it algebraically? Right, it's a very algebraic discussion. What does this look like geometrically? Right? So we already know that a partial derivative, different interpretations, it's a directional derivative, it's a unit directional derivative, right? Different interpretations of those kinds of derivatives. But a very comfortable, let me say, interpretation of a partial derivative, slope of a tangent line to a graph. Right? And that's where very often students really like to hang their hat on that, which, I get. So what is a good geometric interpretation of a second partial? Good news, it's kind of exactly what you think in the case that I just circled. So if you want to take the y partial of the y partial of f, let's keep in mind that when you take a partial with respect to y, you're holding x constant. I can geometrically represent what it means to hold x constant by drawing that plane. Right, that plane slices through this. I've drawn a paraboloid here just to, have something to look at. Slices through this surface to make a curve, And when we talk about the partial derivative, we're talking about the slope of the tangent line to that curve. Okay, fine. So, well, now think about it. If you take the y partial of that y partial, you're again holding x constant, which you already did. You don't need to say the second time that I'm holding x constant, and furthermore, I'm also holding x constant. You're already holding x constant. So really what you're doing is you're saying, I want to hold x constant, and I want to look at this cross-section, and I want to take the second derivative. What's the geometric interpretation of second derivative? We already know that. It's concavity. Right? So just like in a Calc 1 class, once you've decided that you're holding x constant, namely once you've decided that you're looking at partials with respect to y, the second partial is exactly what you think it is. It's concavity. Now specifically, it's concavity of that cross-section. Right? There is a completely different question, which is, what is the second partial with respect to x? Well, second partial with respect to x, let's see if I can draw better. Yeah. Second partial with respect to x, we're going to be holding y constant. And in other words, looking at that cross-section, in other words, asking for what's the concavity of that curve, that cross-section curve, right? So these are not the same thing. In this case, they're both positive. There's no law that says they have to be. Right? You can try to, it's a geometric question. You can ask yourself, can you think of an example where maybe the concavity in the x direction is positive, the concavity in the y direction is negative? You can think of what that might look like. It's kind of a geometric challenge. And something to be thinking about. Pringles. Think about Pringles. Pringles would have this feature. Right. Okay. All right. So let's see. Now here's a harder question, and that is, what do you get when you take what we call a mixed partial, mixed second partial? So here we're not taking the x partial of the x partial or the y partial of the y partial. Here we're going to take the y partial of the x partial. Now our argument breaks down. Our previous argument was, yeah, I've already said I'm holding just one variable constant, and if I take another identical partial again, I don't have to say again that I'm holding the exact same variable constant. I already said I was. Here it's the opposite variable. All right, so for this weird, if you think about it from an algebraic standpoint, it says here, for the purposes of that inside object, I want to consider y to be a constant. And having done that, having now an expression for what I get when I hold y constant and take a partial with respect to x, now what happens if I start to change y while holding x constant? Right? I mean, algebraically, this is hard. How this connects to single variable calculus, pretty non-obvious. Much harder question. Well, there's a nice way to think about this. Works very nicely. We're going to go as follows. I'm going to interpret that, the first partial that I'm computing, the partial with respect to x, I'm going to interpret that as slopes of tangent lines, right? We already know partials are slopes of tangent lines, specifically tangent lines in the x direction, cross sections in the x direction. And this, the next partial that I'm taking, I am not going to interpret as a slope of a tangent line. It's really hard to make sense out of that. I'm going to interpret that secondary partial as a rate of change. Now remember, let's not lose sight of the fact, the fundamental way that you should be thinking about partial derivatives is that partial derivatives are directional derivatives. They're very special directional derivatives, but they're directional derivatives. It says, look, as I start moving in a certain direction, what's the rate of change of the function as I move in that direction? So that's the interpretation I want to take here, which is we're going to be looking at slopes in the x direction, and how do those slopes in the x direction change as I move in the y direction. And here's the picture. I have to zoom out one notch to fit this in. Okay, so here we go. Here's some slopes in the x direction. Let's start with there's a cross section. By the way, you'll notice I didn't draw the surface. It would make the picture a little harder to make sense out of. But there is a cross section in the x direction, representative of taking a partial with respect to x. Right? And let's suppose whatever my surface is, let's suppose that's what the slope of the tangent line. That's the tangent line to the cross section in that plane right there. So that's partial with respect to x. It's that slope. And the act of taking the partial with respect to y of that partial with respect to x says I want to know as I move in the y direction. I'm always taking cross sections perpendicular to the parallel to the x-axis. I'm always looking in the x direction. But as I look in the x direction, having moved further in the y direction, and see now my picture's getting all messed up, but anyway, all these lines are intended to be in the x direction. That first one. As I move in the y direction, how do the slopes in the x direction change? That's what this is saying. Now, what does that look like, right? This is not concavity. It's absolutely not concavity. This is something geometrically very different than concavity. There is no single variable calculus version of this. This is a brand new geometric concept that we've never seen before, right? And you can give it a name. One of the words is torsion. I like to think of this as the way in which the surface is kind of being twisted. You know, you could imagine that, like if you have a sheet of rubber. I'm trying to hold the sheet of rubber by the four corners here. If you had a sheet of rubber, you could talk about what would happen. What would it look like if you twist it one way on one side and the other way on the other side, putting a twist in it, right? So that's what this looks like. This mixed partial measures the twisting of the surface, not a bending down, not a bending up, but a twisting. Anyway, geometrically very interesting. Now, there was a question from the back earlier about, well, what about if you take the partials in different orders? Here I've done the xj partial first and then the xi. Here I've done the xi partial first and then the xj. These are different algebraic expressions. The rules for derivatives are kind of, they're sufficiently cryptic that you wouldn't necessarily consider it obvious that these would always have to equal to each other, but it does turn out that very often it's true. Now, not always, but very often it is true that mixed second partials give you the same value no matter what order you take the derivatives. Now, there is a catch. All of the second partials have to be continuous. Right? If all of the second partials are continuous, then in fact, great news, mixed second partials don't care about the order. And there are counterexamples. I'm not going to talk about the counterexamples here in Math 212. It's not something we need to worry about. So anyway, FYI, those counterexamples do exist. Okay. All right. Okay, so moving along. Bunch of computations I have you doing here. By the way, some of these computations are going to end up being important later on, and some of them will not show up in this course so much, but will show up in later engineering courses, physics courses, chemistry courses that you'll be taking if you're a science major, taking later on. So we're going to talk later on about this thing called divergence. Divergence of a vector field. By the way, we'll talk later about what a vector field is. But anyway, divergence is a quantity that's very geometrically natural and is very important in physics and engineering and chemistry. And it's computed by way of a certain formula that uses partial derivatives. This is one of the reasons why partial derivatives are super important, is they're so easy to compute with that all other kinds of objects, huge numbers of kinds of objects, we write in terms of partial derivatives just because it's so convenient to do so. So likewise, there's a thing that we're going to talk about later called curl, that is computed entirely with partial derivatives because they're so convenient. And various other examples that I have in here. that have various different physics applications. There's this thing called the Laplacian Operator, defined by this formula. Very important in physics, and it's defined in terms of partial derivatives. If you want to understand how heat flows through a heat-conducting object, which is, by the way, if you think about it, not obvious, right? Heat, if you have some object and you make it hot on this side, eventually the heat kind of flows over. But how and at what rate, and how does that work exactly? How do you quantify the flow of heat through, even a one-dimensional rod is hard enough, but what if it's a three-dimensional, like this room that we're in? What if there's a radiator here? How does the heat flow through the room? It's a hard math problem. And it's defined by the heat equation, which is this, which is defined by the heat operator, which you'll notice is defined in terms of partial derivatives. So partial derivatives are it just keeps showing up. If you want to understand how waves work, physicists describe the wave equation to understand that, and it's all in terms of partial derivatives. Okay. All right, so this is just intended to be kind of a preview of things to come, this course and future courses, and also I want you to get a very clear eyeful of how broadly applicable partial derivatives are because of this, how easy they are to compute. Totally awesome. Okay. All right. So let me remind you, here's our definition of directional derivative. Let's take a moment to acknowledge how much this applies to directional derivatives. If you're trying to understand some multivariable function, wherever you might happen to be in the domain, let's say here, whichever direction you might happen to be going, if you want to understand, as I move in the domain, as I move in the input, what's the corresponding rate of change in the output? If you want to understand derivatives as we have conceived them in single variable calculus, this does it, right? Directional derivatives. It works for any function almost any function, at any point, in any direction, at any speed. Aren't we done? Right? What else is there to know about multivariable derivatives? This answers every question that we seemingly could think of in terms of derivatives of multivariable functions. But there's in fact quite a bit more to the story. There's a pattern that holds for most functions, not all, a few exceptions. But for most functions, there's a very strong pattern that holds with these directional derivatives that we have not yet noticed. And I want us to notice this pattern. So here's how that works. Do a quick computation. This is just a computation of a directional derivative. We already know how to do directional derivative. It's a polynomial, yawn, right? This seems like haven't we already done this before? The one twist that I'm going to put on this is, yes, I'm taking a good old plain old directional derivative. Yes, it's a plain old polynomial to which I'm applying the directional derivative. The twist is the velocity I'm going to leave as a variable. Right, so I've got an explicit function. I've got an explicit point. Right, so f given, a given, but I want to understand how do those directional derivatives depend on the velocity. There, but it's hard to highlight such a small thing. Yeah, let me do it like this. How does directional derivative depend on velocity? Okay, so brute force calculation, plug and chug. We'll take all of these givens, and here's my a plus tv. Plug into the polynomial, which becomes that. Take the derivative, a bunch of tedium, and here's the punchline. What a simple little formula. Right? So, up to now, anytime we wanted to compute a directional derivative, well, it was a whole new parameterize the line, plug into the function, take the derivative, set t equals 0. We had to go through the whole algebraic process every time. Now what we have here is, hey, for this function, at that point, I've just done infinitely many calculations. Henceforth, whatever your velocity vector at that point A might be, here's a real easy formula to compute the corresponding directional derivative. Yeah? Okay. How impressive is that? Well, I don't know. It's just plugging stuff in. Here's the neat thing to notice. This is not just any old function. It's got no quadratic terms. It's got no cubic terms. It's a linear transformation. All these directional derivatives are computed with a linear transformation. Now, you might be thinking to yourself, I'm not terribly stunned. Look at the original function we were looking at was quadratic. Isn't it true that the derivatives of quadratics are linear? Well, here's the thing. This works for any polynomial. Now, I don't want us to go through the details of this algebra. The notation's kind of clunky. But this is a generic polynomial. Lots and lots of terms that I'm adding up with coefficients being multiplied by powers of different variables. Generic polynomial. Whatever that polynomial is, go through the same game. The way that directional derivatives depend on velocity is always a linear transformation. This works for any polynomial. It's a real eyebrow raiser. You wouldn't think this would be true, but it is. It's a healthy exercise to try this for don't necessarily look through this tedious algebra I just skipped, but take a cubic, right? You're going to sort of expect that when you take the derivative of a cubic, shouldn't it kind of sort of be a quadratic? And it's not. As the directional derivatives depend on velocity, linear transformation. Okay. So I think it's a healthy exercise for everybody to do at least once. At least one of the homework exercises will have you do that. So I state this as a theorem. For any polynomial, the directional derivatives are computed as a linear transformation. And by the way, this being a real valued polynomial, keep in mind linear transformations are always represented by matrices, but when there's only one output, then effectively that matrix has a single row, and so effectively it's done with a dot product. So this says linear transformation. Okay. So, neat fact. This is such a neat property of polynomials that I think it deserves to have a name. All polynomials have this amazing feature. Oh my God, are you kidding me? Directional derivatives can always be computed with linear transformations. I want to give that property a name. A function whose directional derivatives can all be computed with a linear transformation on velocity. Wow. And the name that we're going to give to that property is that the function is directional linear. Hopefully you see the motivation for the term. That directional, because we're looking at directional derivatives, and linear, because those directional derivatives are computed with a linear transformation. Okay, so restating this theorem now, all polynomials are directional linear. Okay. All right, now I just want to set that idea aside. We have to take a quick discussion here of differentiability. This is a tough word to talk about in a multivariable context. We're not going to give a really full discussion of differentiability. I'm going to talk about several different related ideas. This is arguably the most important one, but it's also the hardest one to talk about because it involves a multivariable limit. And y'all watched about multivariable limits within the last few days, and multivariable limits are kind of weird. Weird things can happen. You come in different directions and you get different answers, and multivariable limits are very strict and delicate and kind of unintuitive and unfriendly. So that's kind of annoying. But it turns out to be the exact right tool to define this very important property. And so I just want to walk you through roughly what this definition of differentiability says, and then we're going to talk about how to get around using it day in and day out, and how we can avoid the awkwardness of this as much as possible. So here's the idea. Let me remind you in single variable calculus a little bit of terminology. Let's see if I can. Yeah, I have some space up here. So in single variable calculus, if you have a curve like that, and if we're looking at a certain point in the domain, right, and then if we move over a little bit and say, okay, what's the value of the function there? There's a couple of related quantities that we can talk about, and I just want to get the lingo straight. If you draw the tangent line, the first quantity you can talk about is how much did the function actually change, right? And this is what we call the increment. And that's the word I want to use here anyway. And as y'all all know from single variable calculus, that's not exactly the same as the linear estimate that we would make. This is called the differential. Right? When you do a linear approximation to a function, you don't get exactly how much the function changed. You get an estimate of how the function changed. And then you argue about how, a certain point of view in single variable calculus, but you let h approach 0, and these become approximately the same thing, derivatives and all that business. Okay, but the first very casual observation is that increments and differentials, not exactly the same thing. The difference between the increment and the differential is right here. That difference, in this case, increment minus differential, or the absolute value of increment minus differential, I'm going to call error. Because, it's how far was our differential off. Right? We wanted to estimate the actual increment. The differential was our estimate. How far were we wrong? Natural to call that the error. Okay. All right. So these objects show up in this thing down here. How much did the function actually change? F of x minus f of a. What is our linear estimate of that quantity? Our linear estimate, now we're hoping that the function could be approximated by a linear transformation. So I'm hoping to be able to apply some linear transformation t, right, just like I did here, right, this directional linearity. I would like to be able to approximate how much the function changed by a linear transformation on the input vector. That's our differential. Therefore, this numerator here is the error. That's a nice interpretation of what's going on in this limit. This limit just says, we've got this complicated thing going on in the numerator, but it's just error. How far off is this linear transformation t from actually getting the right answer in its attempt to approximate the increment? So, error. Okay, now you notice that there's this denominator here as well. So when you divide, let me restate that. Why are we dividing by x minus a here? What's the purpose of dividing by x minus a? I would make the observation that error is, it's unimpressive for that error to be 0. Think about it. What if I had a completely wrong tangent line? What if my tangent line looked like that? Well, then my error would be much larger, but my error would still approach 0. Of course the error is going to approach 0. H is approaching 0. Everything's getting super small. It's not surprising for the error itself to approach 0. Right? So the reason we divide by x minus a is that, let's see, one more I wanted to, there, is because it's actually pretty rare for this, once you divide by x minus a, we call that relative error. It's pretty rare for that to equal to 0. That says we're dividing by, I do color choice here. I'll do it in, I've kind of run out of colors. Orange. When you divide by x minus a, that means that not only does the error have to be getting small, it has to be getting really small. It has to be getting small even faster than the than the dx is, right? And that's a trick. Okay, so if you can make not only the error, but if you can make the relative error approach 0, note that's the requirement. I need this limit to equal to 0. Then that t, that estimate, that differential estimating the increment is doing a good job. So that's the motivation for looking at relative error. This is the definition of a differentiable. A function's differentiable if you can do this. If there is a linear transformation, somehow that will satisfy that limit condition. And the good news is, if so, if a function is differentiable, if you can find a linear transformation that does a good estimate of the function, then it's directional linear as well, which is no surprise, because directional linear means as I'm trying to estimate the function, the result is linear. It's almost like they're saying the same thing, sort of, approximately. Anyway. So, if it's differentiable, it's directional linear. Heads up, though, if it's directional linear, it's not necessarily differentiable. And we'll talk about that in a few minutes. Okay, so if a function, this is a definition here, if a function's differentiable, bad color choice. If a function is differentiable, that means that there is a linear transformation that does this amazing feat. That linear transformation, we call it the derivative transformation of f. We write it like this, no surprise, D for derivative. It's an easy one to remember. And then, of course, we're looking for a linear transformation that accomplishes a certain task. It accomplishes this task at a certain point. So we're taking the derivative of a function, but specifically we're taking a derivative of a function at a point. So you got to tell me what function, what point, before you tell me what the linear transformation is that's estimating it. So that's why then in the notation here you notice derivative transformation, and the subscript has to include both the function and the point. Okay. All right. So now I'm going to write down another equation. This is another one that it's tempting to say, well, of course. This equation here. And students very often look at that and say, I see the same 4 letters arranged differently. Who cares? What's the difference? Why does it matter? And it's subtle. It is subtle. Let me walk you through the differences on this. On the left side over here, what we have is, I'll do that one. Whoops, sorry. On the left side here, it says, I'm looking at this function f, I'm at this point A, I want to approximate how the function's changing at this point A, and I want to find a single thing. I want to find a linear transformation that has this feature that no matter what velocity vector I plug in, that one linear transformation will compute the directional derivative for me. Okay. And very importantly, that's not what this says. Over on the right, this says, if I'm at the point A moving with that velocity, I would like to be able to compute the directional derivative. Now, if I'm at this point A moving with a different velocity, I would like to again be able to compute the directional derivative. And whatever my velocity vector might be, I would like to be able to compute the directional derivative. That is not the same. All those calculations are separate. They're all independent of each other. That's not the same as saying that there is a single linear transformation that will do all of them all at the same time. So that's the big difference. Now we know that polynomials, right? We already know that polynomials always compute by a linear transformation. So that's no issue. But other functions don't. All right. Now, what's the advantage of writing directional derivatives this way? It recovers an old point of view we had on single variable calculus. Remember, our point of view on single variable derivatives was a relationship between input vectors and output vectors. And notice that this one thing now does that. Right? We've previously had things that, if you give me an input, then I can go through some game, some process, the result of which will be to give me the output. But it was a sort of a process, right? Here we have a thing, not a process. This thing, this linear transformation, has the feature that if you give me an input vector, the result is an output vector. One thing does it. Just like a single variable derivative, right? Remember, if you think, flip back to section 4.1. In section 4.1, the motivating perspective that we had on derivative was a derivative is it's a thing that if you give me an input vector, then there's a resulting output vector. This linear transformation does that. So, in a very important way, the linear transformation here, this thing, this derivative transformation, very arguably is the most fundamentally natural point of view on what is a derivative of a multivariable function. Derivative of a single variable function, when you're in a Calc 1 class, you think of a derivative of a function as being a function. Okay, sure, but if we restrict our attention to a single point, derivative of a function is a number. You're accustomed to thinking of derivatives as a number because, of course, you're accustomed to thinking of derivatives as slopes, which, of course, are numbers, right? That's very Calc 1. In a multivariable context, a derivative, my opinion, most fundamentally natural way to think of a derivative is it's a linear transformation. And ultimately, really not such a surprising result because it's a relationship between input vectors and output vectors. That's what linear transformations do. You give me an input vector, I give you an output vector. That's the whole idea of a linear transformation. Certain properties being satisfied, of course. Okay, so anyway, I think this is a big deal, so I'd like to dwell on it for a few seconds there. Okay, we've already done this computation here. Consider that polynomial from our first example. What is the derivative transformation? Well, we already know that directional derivatives are computed by that formula. We've already done the grunt work of computing what is the formula for all the directional derivatives. Well, all that's left is to interpret and realize that this is simply, if I take the right point of view, that is a certain linear transformation applying to my velocity vector v. And that linear transformation, don't forget we represent linear transformations by matrices. That linear transformation is represented by this matrix. So that's the derivative transformation. Everybody on board? And for most functions, you can do calculations like this. You take just compute a generic formula for directional derivative, do this computation here, certain amount of plugging and chugging you got to do, right? The answer is going to be some formula which you then simply recognize as being the action of a linear transformation. Okay, so there's several homework problems where you're going to do something kind of like that. Okay, let me remind you, differentiability is awkward. There's this great big multivariable limit here to deal with. If you want to prove that a function is differentiable, which very often we will need to do, if we have to prove a function's differentiable, do we have to actually deal with this limit? On its face, you would think so. You would think we have to, this is what it says. Differentiable means this. Shouldn't I have to check this? The really good news is that there's a more sophisticated idea that will crush this for us. It's called continuous differentiability. It's very surprising. A function is continuously differentiable if all the partial derivatives exist and are continuous. So this is just a definition. This seems like a poor definition, by the way. We went to a bunch of trouble in defining differentiability, talking about increments and differentials and relative error and multivariable limits, right? The definition of differentiability we were real weird about. Here I'm defining seemingly a more powerful concept, continuously differentiable. and I'm just making some vague references to partial derivatives and continuity. This seems like I'm phoning it in. And the amazing thing is really surprising, but these easy to check things, partial derivatives, world's easiest derivatives to compute. I just have to check that they exist. Okay? We're not dividing by 0 or something, right? And I have to check that they're continuous. No big deal, right? Continuity. We have these extensive theorems from the section in limits that says most functions are continuous. Right? Easy things to check. And check this out. If a function is continuously differentiable, then it's also differentiable. So this is an awesome theorem. This is a huge time saver, effort saver, pain saver. If you want to know if a function's differentiable, side note, it's probably continuously differentiable. Don't deal with the multivariable limit. Oh my gosh, that's work. Check first to see if it's continuously differentiable. It almost certainly is. And once you know by very little effort that it's continuously differentiable, then this theorem instantly tells us, therefore it is differentiable. So this is how business is done. This is how most of the time, except for some weird, obscure examples that we have very little relevance to engineering and physics. If you want to prove a function's differentiable, you check that it's continuously differentiable. For crying out loud. Okay. All right. So a quick example. Here's a multivariable function. How do I prove that this function is differentiable? Well, it has 2 input variables. It has 2 output variables. Therefore, it has 4 partial derivatives. These are just first-order partials. They all exist. They're all continuous. Easily confirmed, right? Borderline freebies. Since it's continuously differentiable, that means that it's differentiable. Didn't have to deal with multivariable limits at all. So anyway, big fan. Okay, so I want to point out just for, I think it's amusing how this turns out. This is what I call a hierarchy of regularity conditions. So we've talked about different kinds of ways in which a function can be nice. We just got through talking about continuously differentiable. Before that, we talked about differentiable. Before that, we talked about directional linear. These are all 3 different properties. Different definitions. This says that there's a linear transformation that computes directional derivatives. This says there's a linear transformation that does something with a multivariable limit. And this says something about partial derivatives and continuity. Okay, so 3 different statements. Here's a couple more. And I think these are pretty easy to motivate. I'm going to call a function directionally differentiable if the directional derivatives all exist. Seems like a reasonable name to give to that property. And partial differentiable if the partial derivatives exist. Okay, so these are all reasonable choices. The interesting thing is there's a hierarchy in that, top down, these all imply each other. All right, so but it's only top down. You can't go up in this diagram. If you know that a function is continuously differentiable, then yes, you can compute the directional derivatives with a linear transformation. If you know that a function is directional linear, then yes, all the partial derivatives do exist. Right? And very often, what we do is, as I just said, you check that a function is continuously differentiable, from which you conclude that the function is differentiable, and therefore I can compute all the directional derivatives by the derivative transformation. That's how we use this most of the time. But there's counterexamples to all of these, to all of the sort of reverse arrows. So there are functions that are differentiable but not continuously differentiable. They're not the same concept. They are importantly different. I'm not going to talk about those examples in this class. There are functions that are directional linear but not differentiable. It's really hard to come up with a counterexample here. It's subtle. If you really want to see one, come to my office hours. I'll show you, but you're not responsible for it in Math 212. This difference, I think, is important. There are functions where you can compute all the directional derivatives you want, but they just don't line up as a linear transformation. So these all exist, but there is no linear transformation that unites them. And I'm going to show you an example. This is the one example I really want to talk about. And here's a graph of it. Kind of a weird looking function. You can't make a piece of paper do this. Paper does not bend in this way. So let's see. I'm going to have to zoom out so I can get the formula on here. Well, anyway. So I guess here's the formula for this function. Doesn't even look that scary. It's especially when you look at it in polar form, r sine 3 theta seems kind of harmless, right? The 3 is a little, what's going on there, right? Because we're not accustomed. Normally we talk about r sine theta, r cosine theta, stuff like that. R sine 3 theta. But anyway, it's fairly harmless looking, and you can even write it in rectangular form, as I did there. And this is what the graph looks like. The weird thing about this is that if you, here's the origin, by the way. Notice I didn't draw the axes, but the axes are like this. There's the axes. If you look at cross sections through the origin, they're all straight lines. All of the cross sections of this are straight lines through the origin. It's kind of weird. So in terms of what this looks like, and by the way, I have a three-dimensional model on this computer. I've given it to my IT guy, and someday soon I'm hoping that he will actually fire up the 3D printer, and I will bring in a 3D model of this graph. It's very weird looking, but what it looks like is you've got a kind of a hill over here, and there's a kind of a hill there, and there's kind of a hill there. But there's kind of a valley down here and a valley down there, and then going around the back, there's kind of a valley down there. So as you sort of, if you from straight ahead, it's like, well, here's the hill, and then there's a valley, and then a hill, and then a valley, and a hill, and a valley, and then back to the original hill. Kind of I don't know how you describe that. I don't think this happens in nature. Anyway, this function is directionally differentiable, because from the origin, if you want to go in, here, let me draw my axes again. If you want to go in any particular direction from here, let's say you want to go, that way. Well, in that direction, the tangent line to the graph, the cross section itself is a straight line. Taking the directional derivative, you're taking derivatives of a straight line. There's no issues. It's super, super smooth. Right? And ditto in any other direction. And yet, if I were to ask you, looking at that point right there, is that curve smooth? Is that surface smooth at that point? And you would have to say, no, there's a super weird kind of it's not a corner. It's not I don't have a word for what that is, but it's something's weird going on at that point. Does everybody see what I'm talking about? So this is another brand new experience. Calc 1 does not have a version of this. There is no Calc 1 sort of like, it's the same thing, higher dimension. No, this is a new concept, peculiar to multivariable calculus. Okay. All right. Okay, moving along. This next section is pretty quick. How are we doing on time? Okay, all right. So the next section is pretty quick, though. Jacobian matrices. So here's where we are. We have this idea of a derivative transformation. Derivative transformations are important because linear transformations are natural and they've showed up. Right? We're trying to understand multivariable derivatives, and in the vast majority of cases, they're computed with linear transformations. Let's just take a second to dwell on that. Derivatives, important concept. We know this is a hugely derivatives. It's like half of the concept of calculus. Derivative. And they're pretty much computed by linear transformation. So this thing is really big deal, right? The derivative transformation. How do I compute it? Right? I don't want to have to spend the rest of my life cranking out directional derivatives straight from the formula. Right? It's tedious. So if there is a derivative transformation, if there is a linear transformation that does this, what is the matrix that represents it? And remember, one of the big upshots of Chapter 3 are what we know about linear algebra so far is that if you have a linear transformation, you can represent it with a matrix. And that's super convenient. So the derivative transformation is important. Therefore, the matrix representing it is important. And we call that the Jacobian Matrix, after the mathematician. So how do we compute the Jacobian Matrix? The question becomes. All right, this is one of my other favorite calculations in the book. It's super cool how everything kind of comes together. So many ideas in such a simple result. If I want to compute this Jacobian matrix, I'm going to do so one column at a time. Don't forget, Chapter 3, one of the big ideas from Chapter 3, columns are images of standard basis vectors. Right? You might say the definition of a matrix is that we compute its columns as being the images of the standard basis vectors. And let's do that. Well, the derivative transformation computes directional derivatives. Right? If our function is differentiable, we know that means that what that derivative transformation does is compute directional derivatives. This is not just any directional derivative. This is a directional derivative where my velocity vector is a standard basis vector. Of course it's a standard basis vector. I'm looking for columns. Columns are images of standard basis vectors. So this being a standard basis vector makes that a standard basis vector, which means, in fact, I'm computing a partial derivative. So the upshot of this, what this argument does for us, this argument tells us that we can understand the most sophisticated point of view on derivatives that there is by way of the world's easiest formula for computing derivatives. So it's just, you couldn't get any better news than this. It's really, really awesome how that works out. So here's how you write that down. Keep in mind what we said as we were computing the Jacobian matrix. This is the matrix that represents the derivative transformations. The columns are partial derivatives. And don't forget, partial derivatives, if you have a vector valued function, right? Let's see here. Where did well, I didn't write it down. Let me write it down. If you have a vector valued function, so function f from Rn to Rm, what is a partial derivative? A partial derivative says I'm going to take f, the values of f are vectors in Rm. That means f has m different components. So I'm going to be looking at all m of these different components and computing the partial derivatives with respect to whatever input variable corresponds to that column. Right. So m different output variables. The partial derivative has m components. Said differently, then this column has m different components, which, by the way, you might say as the matrix has m rows. Constant frustration with matrices, the number of elements in a column is equal to the number of rows. Right, so got to keep that straight. It's easy to kind of mess that up. Everybody on board? Okay. So the nice punchline of this calculation is that the Jacobian matrix, the matrix representing, again, the most sophisticated point of view on derivatives, as a linear transformation, and it's just look, just take all the partial derivatives. take all the outputs, look at the partials with respect to all of the inputs, assemble them in an organized fashion. That matrix is the right matrix. Yeah? Any questions? Couldn't ask for an easier answer, right? Realistically. Okay. All right. Do keep it straight which way it goes. Columns correspond to input variables that you're taking derivatives with respect to, right? So, like you can talk about the x1 column, the x2 column, right? Those are input variables, and columns correspond to input variables. A little bit of foreshadowing. Let me just notice, kind of as it has turned out, output variables. Let's look at these, the partials of F1. All of those F1 terms ended up in the first row. As it turns out, in the same way that input variables correspond to columns, output variables correspond to rows. And we're going to flesh that out a little bit more later, possibly today. Okay, everybody on board? So, by the way, very common mistake that students make is they'll inadvertently transpose this matrix, and it's unfortunate, but it is very important that this gets straight. Very often, students will take the partials with respect to x1 and will make those the first row. That's wrong. It's not the first row; it's the first column. So you've got to make sure to get it straight. Don't inadvertently transpose it. It's wildly wrong. Everybody happy? And then if you find yourself, if conceivably you forget, right? If you're like, oh my gosh, I forgot to study that. Oh no. Which way does it go? I don't want to have to roll the dice 50-50. I get it wrong. Think it through from this calculation. We know columns are images of standard basis vectors, which is where the partial derivatives come from, right? Specifically, partial derivatives with respect to an input variable. So columns correspond to input variables, right there in the calculation. Right? So easy to recall if you forget it. Okay. Okay. So henceforth, if you want to compute a directional derivative, day in and day out, how do people compute directional derivatives? Do they use the formula that I showed you in section 4.3, I guess it was? No, that formula is inconvenient. That formula requires me to parameterize stuff, right? That's effort, right? Overwhelmingly, what people do to compute directional derivatives is they say, look, directional derivatives are computed with a derivative transformation. Derivative transformations are computed with Jacobian matrices, and Jacobian matrices are computed with the world's easiest derivatives, partial derivatives. Compute your Jacobian matrix multiply. Much easier. So let me show you some examples. Here's an example. Now you could even visualize this being a problem from section 4.3. Here, we've got a function of 2 input variables, 3 output variables. How would I compute the velocity of the output? Or said differently, how would I compute the directional derivative? Right, if I'm at a certain input point in the domain, so we're at that point. And let's see, let me color code better here. We are moving with this velocity. How would I compute? And we're looking at this. Color choices. This function. How do I compute how fast the function's changing? So directional derivative, right? For sure. This could be a section 4.3 problem. Compute that directional derivative. You take the point and the velocity and you make a parametric line and you plug into the blah, 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 and you get this great big monster because look at that function on the right there. It's kind of long. Right? Okay. So you could, though, brute force this problem. Instead, let's argue as I just stated, and most of this ends up being implicit when you actually do this. Step 1, directional derivatives are computed with a derivative transformation. Right. derivative transformations are computed with Jacobian matrices. Jacobian matrices are computed with partial derivatives, which are super easy to compute. Right? So I just did 6 partial derivatives. Now those are easy partial derivatives, right? You take the original function here, take the 3 partials with respect to x. Let's do these one at a time. The partials with respect to x, sine y, negative y sine x, and 2xy cubed. First column. All right, so first input variable, first column. Likewise, second input variable, partials with respect to y, x cosine y, cosine x, 3x squared y squared. Second column. All right, so input variables that you're taking partials with respect to give you columns of the Jacobian matrix. Super easy to write down. Multiply the Jacobian by the velocity vector. A little bit of matrix multiplication, plug in, a little bit of arithmetic, bam, you're done. You don't have to parameterize anything. Everybody on board? Okay. All right, there's one little warning I want to give you about there is a possible landmine to step on. Let's go back to this formula here. A lot of students will oversimplify. As powerful and ultimately simple as this is, a lot of students will oversimplify as follows. Very often students will say, oh, okay, so all I have to do is compute these partial derivatives and matrix vector multiply, and I can compute any directional derivative on planet Earth. And again, it's not quite true. In order to compute what I have written here, let me be careful with my language. In order to compute that, all you have to do is to be able to compute partial derivatives. Partial derivatives are easy to compute, but if all you know is that you can compute partial derivatives, then all you know is that your function is partial differentiable. Right? So that's a little bit of a worry. You can't just say, oh, I have computed all my partials and I've assembled them into a matrix, and then start talking about how the function's differentiable and you can compute with a linear transformation and that the matrix multiplication means something. No, it does not follow, right? You cannot do that. So what you have to do, it's surprisingly small amount of fix, but yeah, you got to make sure the partial derivatives exist in order to create your Jacobian matrix in the first place. After you confirm that the partial derivatives exist, also confirm that they're continuous. This is easy to do. You just have to look and say, oh, by the way, these are all continuous. Once you've confirmed that they're all continuous, then you know your function is continuously differentiable, and then you can matrix multiply and it actually means something. Okay. So there is a homework exercise in the back of the Jacobians section here that hinges on this. And so we have a hypothetical. Here we go. You'll recognize this function. This is the weirdo function that has a strange, it's not a corner, it's not a, I don't know what to call it, but something weird is happening at the origin there. This weird function, you can compute the directional derivative, you can compute the partial derivatives, and they're not even hard. It's easy to compute the partial derivatives. And then once you know the partial derivatives, you feel like, well, doesn't that give me the Jacobian matrix? And if I know the Jacobian matrix, can't I compute any directional derivative as a result? And the answer is with this calculation is a little too fast and loose with regularity. This calculation is assuming that the function is differentiable, which it isn't. Right? And we know it's not because we already showed it's not even directional linear. Yeah.
So if we run across that, at that point, will we just try and move up the hierarchy from the bottom?
If you find that your partial derivatives are not continuous, or if you're having trouble computing the partial, if something is disturbing and possibly weird, then you seem to be worried. You might just resort to computing your directional derivatives directly. It depends on the circumstance, right? Because there's lots of different possibilities. But it's something to be watched out for. The good news is that overwhelmingly, most commonly, what's going to happen is that you can compute your partial derivatives and they are continuous. So vast majority of the time, it's just not an issue. Yeah. Okay. All right. Okay, so moving on to the next section. This next section is about a neat special case that happens sometimes. Ultimately, this is about Jacobian matrices, kind of. So let me just observe that if you have a function like this, now what's interesting about this function is that the target is R1, so there's a single output variable. So again, this is what we call a real valued function, because the output values are simply real numbers. Okay, so real valued function. If you have a real valued function, well, okay, you have several different input variables. For each of these input variables, you're going to talk about the various partial derivatives, but each one has only one output component, and therefore there's only one entry in each of these columns. Or said differently, there is a single row in this Jacobian matrix. So, neat fact to observe, if you have a real valued function, the Jacobian matrix has a single row. I mean, it has various columns corresponding to the various input variables, right? But one output, one row. All right. So, if we take this Jacobian matrix and do what Jacobian matrices do, right, you write down the Jacobian matrix. We compute directional derivatives with the derivative transformation, namely by multiplying the Jacobian by vectors. You get this formula here. And this expression here, I mean, this is kind of an innocent observation I'm going to make here, but we compute that with a dot product, right? I mean, there's different ways to think about how to compute a matrix vector multiplication, but wouldn't it seem weird at this stage when there is, in fact, a single row? Wouldn't it seem weird to view this matrix multiplication as a linear combination of columns? That just seems strange. Why would I view this as a linear combination of real numbers? Right? It's much easier to view it as the old high school point of view as a dot product of the vector in question with the various rows, in this case only one row of the matrix. Right? So, innocent observation there that in this one case, the matrix vector multiplication happens to be a dot product, and then we get this handy formula here for how to compute directional derivatives. Neat fact, real valued function, you can compute directional derivatives with a dot product. Is everybody on board with that? Any questions about how I got there? Now you might be wondering, how's this a win? What does this buy me? I mean, it is in fact ultimately exactly the same arithmetic to do that or to do that. If it's exactly the same arithmetic, why bring it up? Right? Why give you a second formula to remember if it doesn't have anything that distinguishes it from the first formula? It's a valid gripe. I am going to come back and talk about that in a second. But before I do, let me proceed with a little bit of terminology. The vector that you get here, this vector that you get by taking the Jacobian matrix and turning it sideways. It ended up being an interesting thing. We call this the gradient vector. The gradient vector of f at the point A. People talk about gradient vectors all the time. I'm going to show you some neat properties of the gradient vector. That'll come up in a moment. But anyway, that's what the terminology is. Here's the notation. Please do be careful with this little symbol here. That little symbol is a triangle. But very importantly, it points down. It is not the same as this. This is not an acceptable alternative, and it's not. Oh, you can't say, oh, well, that's just how I make my triangles. Nope, that's a different thing. That's a very, very different thing. In fact, look back to the section on partial derivatives in the exercises. We define this very, very, very different thing here. So you have to be ultra careful. Make sure to draw your triangles the right way. And again, with all the new symbols that we've introduced, you can sit there and, spend a few minutes, just like you did with partial derivatives, sit there and crank out, 50, 60 of them. Make sure that you're comfortable making them. Likewise, try to get good at making these little triangles. So that's the notation that we use. Okay, so now back to the question of, why do we care? Why do we care that I can now, for a real valued function, I can view this as a dot product instead of a matrix product? Here's why I care. Subtle point. The subtle point is that because this is a dot product, this is something about which I already know geometric facts. Right? I already have geometric sort of intuition. We know geometric properties of the dot product. We don't really know any particularly strong geometric properties of matrix vector multiplication. Right? We know how to do it. We know what it represents in a way, but it's more of an algebraic thing. The dot product is very geometric. So what's going to happen, and again, this has already happened multiple times in this class, and it's going to keep happening, but when you find an equation that involves something that you know about, in this case the dot product, right, then that's an opportunity for you to use that connection to figure out things about this new object that you don't know about. Right? Okay, so we ended up understanding cross product by way of its connection to determinant, right, and that kind of thing. Okay. All right, so we're going to come to understand the gradient vector by taking advantage of the fact that we know about the dot product in this formula. And yeah, sure, we got 30 seconds. Let's go ahead and call it a day. I'll end early instead of late for once. Okay, see y'all later.